expectation. How much are you expected to win or lose when you are either the dealer of a game or the player of a game? Okay? So first of all, let's think about this. If the dealer is expected to make 50 cents every time somebody plays, then the player is expected to lose 50 cents every time that they play. Okay, so we have that straight. Now, what we're going to do for mathematical expectation is this. We are going to figure out the probability for each scenario. Okay? What is the probability of winning? What is the probability of losing? What is the probability of breaking even? Okay? So, let's say it costs $1 to play the game, and you lose, you walk away, and you are down $1, right? You lose $1, okay? If it takes $1 to play a game, and they give you $1, you have broken even, right? If it costs $1 to play, they give you $2, you have won $1, okay? Those are things that we are going to consider for mathematical expectation. What's the probability of losing $1? What's the probability of walking away with $0? What's the probability of winning $1? And then what we're going to do is we're going to multiply those. What's the probability of losing $1 times -1? What's the probability of breaking even times 0? What's the probability of making $1 times 1? And then when you add those all up, that gives you your mathematical expectation for playing a game. So our first example is roulette. Okay. And this is just a very basic roulette example. Okay. There are 38 slots, 1 through 36, plus 0 and double 0. Half the slots from 1 to 36 are red, the other half are black, 0 and double 0 are green. A player places a $1 bet on red. If the ball lands in a red slot, the player gets the original $1 back plus an additional $1 for winning the bet. If the ball lands in a different colored spot, they just lose. So this is just one scenario. This is the probability of coming up to a roulette table, betting on, what did I say, red? Yes. Mm-hmm. Okay. So, first of all, what is our sample space? We could land on what colors?
Red, black, green.
We could land on red, black, and green. The numbers aren't important because there is no stipulation on me winning or losing based on those numbers. Okay? The probability of winning. We win if we land on red. How many red spaces are there?
18.
There are 18. So the probability of winning is 18 out of 38. We can reduce it, but I'm not going to right now. Okay. What is the probability of losing? How many spaces are losers for us?
20.
20 out of 38. Okay. So then this table up here, this is what I call a probability distribution, and it'll really lay things out nicely for finding our mathematical expectation. Okay, so we have value and probability. Still mining. I thought it stayed all together. Hey, look at that. Okay, so we could pay $1 and walk away empty-handed. That would mean we lose $1, -1. Or in Friday's case, a Tootsie Roll. Okay. What's the probability of losing $1?
20 out of 38.
20 out of 38. Okay. Or we can walk away Okay, we could walk away with $2, but that would mean we are only gaining 1. If you get your dollar back, that's breaking even. Getting another dollar, we're plus 1. And the probability of that is 20 out of 38. Now, oh, thank you. I was thinking of what I wanted to say next instead of looking at the right number. There we go. Now, in your probability distribution, it has all of the options. Okay? So that your probability should add up to what number? 1. If every single option of winning, losing, breaking even, whatever, is in your probability distribution, then your probability should add up to 1. It has everything that could happen. This is a very simple example. We only have 2 probabilities, but you can see that those obviously add up to 1. Okay? So, if we want our mathematical expectation, we're going to take -1 times the probability of getting -1 and add it to +1 times the probability of gaining 1. Okay? So without a calculator, we can obviously see that this is going to be -2 over 38, right? Which is -0.0526. And I'll tell you why I did that many decimal places in a little bit. Okay? What does this mean? We just calculated the mathematical expectation for the player. If I walk up to this table, every time I play, I am expected to lose 5 cents. Now, we know that's not realistic, that if we go up and we play one time, we're going to lose 5 cents. No, we can either make $1 or lose $1. However, as we play, the more and more and more we play, it's going to even out to where you're only losing 5 cents per time. Okay?
If the probability was perfect, how many times would that be?
Okay. It just depends. Now, we would have to play this hundreds and hundreds of times in order for it. Like, the more we play, the closer we get to that number of each time is 5 cents we lose. Does that make sense? If we play it 3 times.
If we played it 38 times, it came out perfect.
If we played it 38 times, it would be close, but it would probably not be perfect. Okay? Now, if you played this game 100 times, how much would you expect to lose? We would take this mathematical expectation times how many times you played, and we would lose $5.26. Okay? Now, some of you may say, okay, that's not so bad. If I play roulette and I just bet on red, if I play 100 times, I'm only going to lose $5. You're still losing money. Are you going to win some? Yep. Are you going to lose some? Yep. And over the course of time, you are going to lose more money than you make. Okay? To be exact, you're going to lose 5 cents every time you play. Okay? Now, what is the mathematical expectation for the dealer?
90.
They're going to gain 5 cents every time somebody comes to play. Okay? So every 100 times, the dealer should be making $5.26 if they're betting on red. Okay? No, it's really not good profits. But is it a profit?
Yeah.
And that's the point. It's a profit. They're making money off of it.
And that's excluding the fact that they're already getting paid to be in there.
Not a lot.
It's their tip money.
Okay?
You can tip the dealer like, hey, dealer is doing.
Are there any questions on this example?
Give him
When they have a computer, the person runs the table,
Isn't this interesting though?
I'm gonna buy casino now.
Yeah, casinos make games in their favor, but they make it so it's enticing enough where, you know, you win some, but then if you look at over time,
I'd say like if I win 5 though.
Seems like math teachers on gambling.
read through example 2. We have envelopes, right? Okay. How many envelopes do we have? We have 10 envelopes. We have 6 that contain $1, right? One, two, three, 4, 5, 6. Then we have 2 that contain 5. 1 that contains $10 and 1 that contains $20. Okay, here's where it gets interesting. A player pays $5 and is able to select 1 envelope. Okay. What is the probability of winning? How many out of the 10 times will a player actually win? 2, right? However, what's interesting about that, are they both times out of 10, are they winning the same amount? No, so that we're going to see that in our probability distribution. Okay, be careful here. What is the probability of losing?
8 out of 10.
6 or 8? 6. Because what's happening here? You're breaking even. Okay, so there are actually 4 different amounts of money that we could either win or lose or break even with. Okay, so since there's 4 different types of outcomes, we're going to have 4 different columns. Columns in our probability distribution. So we have value and probability.
Oh, I just freaking.
I never leave myself a number. Okay, so if we place $5 down and we get a dollar envelope, Tori, how much are we down? Yes. So our value is -4, and we decided that probability was 6 out of 10. Okay. We pay $5, we get $1. So we're down 4. It's exciting, we won, but no, we really didn't. Right? Okay. Then we have 2 $5 bill envelopes. So there's a probability of 2 out of 10 that we get one of those. And Finn, we're walking away with nothing. Okay. There is 1 $10 envelope. So I know the probability of winning is 2 out of 10, but we have to split it up. There's a 1/10 chance that we walk away with $5. And there's a 1/10 chance that we walk away with $15. Okay, remember we paid $5, so if we get the $10 envelope, we're up 5. We paid 5, if we get the $20 envelope, we're up 15. Okay. After lunch, we will discuss the mathematical expectation. So the mathematical expectation for the player. We are going to take each probability and multiply it by its corresponding value. So -4 times 6/10. That's the probability it goes. Plus 0 times 2/10. Yes, I know that's 0, but I still want you to write it. Okay. +5 times 1/10 plus +15 times 1/10. What is our mathematical expectation?
0.4.
I don't have a lot of room, so I'm going to write -0.4. Let's interpret that. Every time you play this game, you will lose 40 cents. Every time you play this game, you are expected to lose 40 cents. The dealer, every time somebody plays the game, the dealer is expected to gain 40 cents. Okay? So,
Is that 40 cents per dollar then?
40 cents per game. So, yes. If you're paying, well, you're paying $5 to play. Yeah. So it's every time you play. So if you play 100 times, you take -4 times 100, -0.4, and you're expected to lose how much? Okay, that sounds like a lot of money now, doesn't it? You're expected to lose $40. I'm an adult and $40 plenty for this place. Okay. All right. Are there any questions? I want to give you some time to start this worksheet. Okay. There are 1, 2, 3, 4, 5 games where I'm going to ask for the sample space, probability of winning and losing, really the 6 things that we found here, okay? And then when you are all done, you're gonna consider, are any of the games fair? Which game is the best to play? Which game is the worst? Those sorts of things, okay? Now, let's talk about a fair game. What would be considered a fair game?
You were losing 0.
50-50 chance
Well, let's think of it as mathematical expectation. I like where you're going with the 50-50, but a fair game would be more that you are expected to break even every time. Okay, the dealer's not making money, you're not losing money. Okay, so a fair game would be considered even, because you could take like a 50-50 shot, like a coin flip, and you could.
Heads I get $1, tails I lose $1.
Well, that would be a fair game, but heads I get $5, tails I lose $1. That's no longer a fair game. That's unfair, and the play is fair, right? Okay, so you'll want to do this on a separate sheet of paper. Okay. We have like 20 minutes, so my hope is that you can get maybe 2 of these done before you leave. I'll come around and I'll check your work as you go. And then in the last couple of minutes, I'll explain to you what's going to happen tomorrow.
So, I believe